In the previous lecture, I have introduced the concept of interval estimation, confidence intervals with a certain confidence level. We have also discussed a method, that is the method of pivoting for obtaining confidence intervals for particular confidence levels. Now, what I want to mention is that the theory of uniformly most powerful tests or uniformly most powerful unbiased test is intimately related with the theory of uniformly most accurate confidence intervals or uniformly most accurate unbiased intervals. So, we restrict attention to the non randomized tests, and then we have the following result. So, let us consider say hypothesis testing problem, say theta is equal to theta naught against some alternative. Actually, that alternative I am not writing specifically, it could be say theta naught equal to theta naught, theta less than theta naught or theta greater than theta naught, etcetera. Okay. Any of the alternatives can be there. Okay. That means, based on any of the alternatives, the rejection region or you can say the alternative hypothesis set will be, for example, here in the acceptance region you have theta naught, in the rejection region you may have all the points except theta naught, or you may have all the points below theta naught, or you may have all the points above theta naught. Okay. Let us consider say a theta naught as the acceptance region. Acceptance region at level alpha, and let us consider say S x to be the set of parameters theta such that x belongs to a theta, then S x is a family of confidence sets for theta at confidence level 1 minus alpha. That means, if I am having critical region or you can say a level alpha test, and if I consider the acceptance region for that, then from there I can derive 1 minus alpha level confidence set. Okay. Now, moreover, if a theta naught is uniformly most powerful for this problem, then S x minimizes p theta theta prime belonging to S x for all theta belonging to alternative hypothesis set. As I mentioned here, it could be all the thetas other than theta naught, it could be thetas less than theta naught, or it could be theta greater than theta naught, etcetera. Among all 1 minus alpha level that is S x is uniformly most accurate confidence region. Let me look at the proof of this. Of course, it is very simple because we are just following the definition. So, if I say theta belongs to S x, then this is equivalent to saying that x belongs to a theta. So, the probability of theta belonging to S x, that is S x including theta, is same as probability of x belonging to a theta greater than or equal to 1 minus alpha. So, what does it mean? It means that if a theta is the acceptance region of a alpha level test, then S x will be a family of confidence sets of 1 minus alpha level. That is one thing. Now, next let us to prove that uniformly most accurate. So, if S star x is any other family of 1 minus alpha level confidence sets, let us define say A star theta that is equal to x such that theta belongs to S star x. Then P theta x belonging to A star theta that is equal to P theta theta belonging to S star x that is greater than or equal to 1 minus alpha. And also, since A theta naught is UMP, we have that P theta x belonging to A star theta naught is greater than or equal to P theta x belonging to A theta naught for any theta in the alternative region of the alternative hypothesis. So, probability of theta naught belonging to S star x is greater than or equal to probability of x belonging to A theta naught, that is P theta theta naught belonging to S x for all theta belonging to alternate region. So, this proves that the S x family is the family of uniformly most accurate confidence regions or confidence sets. Let me consider one example here. Say x 1, x 2, x n, this follows 1 by sigma e to the power minus x by sigma. And let us consider the testing problem. Sigma is equal to sigma naught against sigma is greater than sigma naught. Now, in this problem we have derived, see this is one parameter exponential family. If I consider the joint distribution of x 1, x 2, x n, the joint distribution that is 1 by sigma to the power n e to the power minus sigma x I by sigma. So, this is one parameter exponential family, t is equal to sigma x I. Let us call it t is equal to sigma x I, and that follows gamma distribution with parameters n and sigma. Okay. This is one parameter exponential family. Therefore, and also you are having minus 1 by sigma, which is strictly increasing in sigma. So, theta is equal to minus 1 by sigma. Therefore, the test will exist. The test will be actually rejecting in favor of the larger value of t. So, the uniformly most powerful test will reject H naught if t is greater than some c, and then we determine this thing. Actually, you look at the distribution of twice sigma x I by sigma naught, let me call it W. So, that will follow a chi square distribution on 2 n degrees of freedom, because what is the distribution of t? The distribution of t is 1 by sigma to the power n gamma n e to the power minus t by sigma t to the power n minus 1. So, if I consider this is under H naught. So, if I consider 2 t by sigma naught, then the distribution of f w, that will become equal to 1 by gamma, same thing. So, that will be the density of chi-square distribution on 2 n degrees of freedom. So, we can write reject H naught if 2 t by sigma naught is greater than say C star, where C star is nothing but chi-square 2 n alpha. Okay. So, the acceptance region for UMP level alpha test is 2 t by sigma naught less than or equal to chi square 2 n alpha. So, by the previous theorem, which we call theorem 2, say we can call this as theorem 2. Uniformly most accurate 1 minus alpha level confidence set is of the form sigma such that twice sigma x I by sigma is less than or equal to chi square 2 n alpha. So, you can simplify this condition here, twice sigma x I by chi square 2 n alpha less than or equal to sigma. That is, we are saying twice t by chi square 2 n alpha to infinity. This is 1 minus alpha level one sided confidence interval actually for sigma. So, the theorem the theory of UMP test is intimately connected with the theory of finding out uniformly most accurate tests. So, particularly when we are dealing with the one parameter exponential families etcetera, then straightforwardly we can translate the acceptance region into a confidence interval by replacing that parameter theta naught or theta whatever we are saying by a general parameter there. Now, also I talk about the shortest length confidence interval. So, let w x theta be pivot and we are choosing say w 1 and w 2 such that this is equivalent to some interval so that the length of the interval b x minus a x is minimum. So, this is our interest. For a fixed confidence level, we would like to have the shortest length. As I mentioned, if I am giving a two statements, for example, I am looking at the rate of cure by a certain medicine. So, we say we are 95% sure, or we can say we are 95% confident that the rate of cure by this medicine is at least 75%, and second statement is we are 95% confident that the rate of cure is more than 80%. Then which statement will be better? Obviously, the second statement is better because it is giving a shorter interval. So, the problem of determining shortest length intervals is of interest. So, we say this is the then Ax to Bx, this is called shortest length confidence interval for confidence interval with label 1 minus alpha. Of course, it is based on this w. If we change the w, we may get another interval here. So, let us look at the examples here. So, if we are considering x 1, x 2, x n following normal mu sigma square is known, then based on x bar minus mu root n by sigma, this follows normal 0 1. Since the normal distribution is symmetric, if I consider a symmetric interval around 0, this will have the highest probability. If I consider a non-symmetric interval, then the length will increase. Therefore, the shortest interval will be a symmetric interval about this. So, that if you use this logic, then we get minus z alpha by 2 less than root n x bar minus mu by sigma less than z alpha by 2, that is equal to 1 minus alpha, which gives the interval x bar minus sigma by root n z alpha by 2 to x bar plus sigma by root n z alpha by 2, that is as x bar minus sigma by root n z alpha by 2 to x bar plus sigma by root n z alpha by 2 as 1 minus alpha level confidence interval for mu. Similarly, when we are considering sigma square is unknown, in that case based on square root n x bar minus mu by s, the shortest length one minus alpha level confidence interval for mu is x bar plus minus s by root n t alpha by 2 n minus 1. Let me solve it as an optimization problem also. I will explain it through an example where let x 1, x 2, x n be a random sample from uniform 0 theta interval. So, we consider say t is equal to x n, and here we can use the pivot quantity as x n by theta. We have actually seen the distribution of this is n w to the power n minus 1. So, we may consider an interval of the nature say w 1 less than x n by theta less than w 2 is equal to 1 minus alpha. So, this implies probability of this is equal to 1 minus alpha. So, what is the length of the interval? Length of the interval is x n into 1 by omega 1 by minus 1 by omega 2. Let me write it as equal to say L, and at the same time this condition will imply that W 2 to the power n minus W 1 to the power n is equal to 1 minus alpha. Let me call this condition as 1. So, we want to minimize L subject to the condition 1. Okay. Now, let us consider differentiation of this with respect to say omega 2, then that will give me x n 1 by omega 2 square minus 1 by omega 1 square d omega 1 by d omega 2. But what is d omega 1 by d omega 2? Let us consider also differentiation of this condition. If I differentiate this, I get n omega 2 to the power n minus 1 minus n omega 1 to the power n minus 1 d omega 1 by d omega 2 is equal to 0. But this condition will give me d omega 1 by d omega 2 is equal to omega 2 by omega 1 to the power n minus 1. If I substitute it here, I get this as equal to x n 1 by omega 2 square minus 1 by omega 1 square omega 2 by omega 1 to the power n minus 1. So, I can simplify this and I can write it as x n into omega 1 to the power n plus 1 minus omega to the power n plus 1 divided by omega 1 to the power n plus 1 omega 2 square. Now, also if we see from this condition, I can consider it as x n and of course, this denominator term will come here. The numerator term I can substitute here. See, from here the value of omega 1 to the power n, I can put it in terms of omega 2. So, this becomes omega 2 to the power n minus 1 minus alpha minus omega 2 to the power n plus 1. This I can write as x n and then w omega 2 to the power n omega 1 minus omega 2 minus omega 1 into 1 minus alpha divided by some term. This is clearly negative because omega 1 is less than omega 2. So, what it means? So, L is actually decreasing in omega 2. So, minimum will occur at maximum value of omega 2. Now, what are the ranges of omega 1, omega 2? Because here I have taken this and the range of this distribution is 0 to 1. So, the maximum value of omega 2 can be equal to 1 only. So, that is omega 2 is equal to 1. If I have omega 2 is equal to 1, then this will give me from 1 we get 1 minus omega 1 to the power n is equal to 1 minus alpha, which gives me omega 1 is equal to alpha to the power 1 by n. So, x n to x n divided by or you can say multiplied by alpha to the power minus 1 by n. This is shortest length confidence interval with confidence level 1 minus alpha. This is based on x n. So, here I have shown through direct optimization that this is the shortest length interval here. I have actually minimized the length of the interval here. Let me give one more example here of an exponential distribution. let x1, x2, xn be a random sample from an exponential distribution with PDF e to the power say mu minus x for x greater than mu. Now, this example we have considered here. If I consider x1, this is minimal sufficient here. And we can consider the pivot quantity W is equal to x1 minus theta. This can be taken as pivot. The distribution of W will be the distribution of W is f W equal to n e to the power minus n W, where W is positive, it is 0. So, we take probability of say 2 points A less than W less than B, it is equal to 1 minus alpha. Now, in this distribution if I integrate out, this condition is equivalent to saying e to the power minus n A minus e to the power minus n B is equal to 1 minus alpha. This is condition 1. Now, based on this, when we are considering the confidence interval, this is becoming x 1 minus theta less than b is equal to 1 minus alpha, which is equivalent to probability of theta less than x 1 minus a and it is greater than x 1 minus b, that is equal to 1 minus alpha. So, here length of the interval b minus a, and we want to minimize this. Suppose I want to minimize with respect to a here, then I will get d b minus del a minus 1. Now, if I differentiate this relation, I will get minus n times e to the power minus n a plus n times e to the power minus n b del b minus del a equal to 0. Now, from here del b by del a, that will be turn out to be e to the power n times b minus a. So, this will be equal to e to the power n b minus a minus 1. Obviously, since b is greater than a, this is positive. So, this is greater than 1, that means this is greater than 0. So, L will be minimized for minimum value of a, that is a is equal to 0, because I am considering the interval from a to b for W and the range of W is greater than 0. So, the minimum value of a that can be simply 0 itself. If I put a equal to 0 in this one, this will give me 1 minus e to the power minus n b is equal to 1 minus alpha. That means, b is equal to minus 1 by n log of alpha. Of course, this is positive, because alpha is a number between 0 to 1. So, this is positive. So, the interval that we will get here x 1 plus 1 by n log of alpha to x 1. This is shortest length 1 minus alpha level confidence interval for mu. This is based on x 1. So, here I have shown that directly by considering the minimization of the length of the interval subject to the condition that we are achieving a certain confidence level, it is possible to derive the shortest length confidence interval. Now, I will also consider the situations where in the testing problem we had considered where UMP test does not exist. Therefore, we were trying to find out UMP unbiased test also. Now, corresponding to that, here we have UMA unbiased confidence intervals. So, what is an unbiased confidence interval? Let me define that. A family Sx of confidence sets for a parameter theta is said to be unbiased at confidence level 1 minus alpha if probability of theta belonging to Sx is greater than or equal to 1 minus alpha and p theta theta prime belonging to Sx is less than or equal to 1 minus alpha for all theta and theta prime, where of course theta is not equal to theta prime. So, this is a 1 minus alpha level confidence set, and in case Sx is an interval, then this will be called, if Sx is interval satisfying these conditions 1 and 2, then it is unbiased confidence interval. So, what is the actually interpretation of this? What we are saying here is that if the true value is theta, then the true value is included in the confidence set with probability at least 1 minus alpha, and if theta is the true value, then theta prime is a false value, then that value is included with probability less than or equal to 1 minus alpha. That means, this confidence interval will actually cover the true parameter value with a higher probability than a false parameter value. That means, the value which is true should have a higher chance of getting included in the interval rather than the and the false value, that is the wrong value, should have less chance of getting included. So, this is a natural condition of unbiasedness. As in the testing problem, you remember the unbiased test was that beta phi theta is less than or equal to alpha for theta belonging to null parameter space, and for alternative it was greater than or equal to alpha. So, similarly, here it is based on 1 minus alpha. Okay. Now, there is a direct relation with the UMPU test, that is the uniformly most powerful unbiased test, with UMAU, that is uniformly most accurate unbiased test. I will state this result here. So, these results etcetera, they are from Rohatgi and Saleh's book, the statements of the theorems and also the discussion and proofs of those theorems. Let A theta naught be the acceptance region of a UMPU size alpha test of h naught theta is equal to theta naught against say h 1 theta is not equal to theta naught. Then Sx is equal to theta such that x belongs to a theta. This is a UMA unbiased family of confidence sets at level 1 minus alpha. Let us look at the proof of this. since A theta is the acceptance region of an unbiased test P theta theta prime belonging to S x, that is equal to P theta x belonging to A theta prime is less than or equal to 1 minus alpha. That is the probability of rejecting when H naught is true is the same as this, that is equal to less than or equal to 1 minus alpha. So, S x is unbiased. To show that it is UMA, let us consider S star x be any other unbiased 1 minus alpha level family of confidence sets, and we write here A star theta is equal to x such that theta belonging to S star x. That means, the corresponding acceptance regions are denoted by A star theta. So, probability of x belonging to A star theta prime, that will be probability of theta prime belonging to S star x, that is less than or equal to 1 minus alpha. So, we can say that A star theta is the acceptance region of an unbiased size alpha test. Therefore, we can write the statement that probability of theta prime belonging to S star x is equal to x belonging to A star theta prime, that is greater than or equal to P theta x belonging to A theta prime, that is equal to P theta theta prime belonging to S x. So, this inequality is there because of UMPU test. So, this proves that this is the uniformly most accurate region here. Now, I will consider certain confidence intervals for parameters of normal populations. I have already given the confidence intervals for the mean of a normal population, both when the variance is known or unknown, and also for sigma square when the mean may be known or unknown. Now, let us consider two sample problems. Okay. Confidence intervals for parameters of two normal populations. Let us consider, say, x1, x2, xm be a random sample from, say, normal mu1 sigma 1 square population, and y1, y2, yn be a random sample from, say, normal mu2 sigma 2 square population, and assume that these two samples are independent. Let me call it x sample and this is y sample. Let x and y be independent. Okay. We are interested in finding out confidence interval for say mu1 minus mu2. Let us take the first case when sigma 1 square and sigma 2 square are known. If they are known, we can formulate nicely the pivot quantity. The distribution of x bar is normal mu 1 sigma 1 square by m. The distribution of y bar is normal mu 2 sigma 2 square by n. So, the distribution of x bar minus y bar is normal mu 1 minus mu 2 sigma 1 square by m plus sigma 2 square by n, and therefore, x bar minus y bar minus mu 1 minus mu 2 divided by square root of sigma 1 square by m plus sigma 2 square by n. This has a distribution free from the parameters. So, this can be considered as the pivot quantity. So, W can be taken as pivot, because this involves mu 1 minus mu 2 and random variables, and the distribution is free from the parameters. So, if I consider the shortest length confidence interval based on this, then I should consider z alpha by 2 and minus z alpha by 2 points. So, probability of minus z alpha by 2 less than or equal to W less than or equal to plus z alpha by 2, that is equal to 1 minus alpha. This is equivalent to the statement x bar minus y bar minus square root sigma 1 square by m plus sigma 2 square by n z alpha by 2 less than or equal to mu 1 minus mu 2 less than or equal to x bar minus y bar plus square root sigma 1 square by m plus sigma 2 square by n z alpha by 2, that is equal to 1 minus alpha here. So, x bar minus y bar plus minus square root sigma 1 square by m plus sigma 2 square by n z alpha by 2. This is 1 minus alpha level confidence interval for mu 1 minus mu 2. But if sigma 1 square and sigma 2 square are unknown, we cannot use this. In that case, we consider another pivot quantity, sigma 1 square and sigma 2 square is equal to sigma square, but unknown. Now, these statements are true that x bar follows normal mu 1 sigma square by m and y bar follows normal mu 2 sigma square by n. But at the same time, let us also consider say m minus 1 s x square or s 1 square by sigma square, that follows chi square distribution on m minus 1 degrees of freedom, and n minus 1 s 2 square by sigma square, this follows chi square distribution on n minus 1 degrees of freedom, where s 1 square denotes 1 by m minus 1 sigma x I minus x bar whole square, and s 2 square denotes 1 by n minus 1 sigma y j minus y bar whole square. That is the two sample variances, and these are all independent random variables. All these variables are independently distributed. If they are independently distributed, I can consider say m minus 1 s 1 square plus n minus 1 s 2 square by sigma square, that follows chi square distribution on m plus n minus 2 degrees of freedom, and therefore, I can write down x bar minus y bar minus mu 1 minus mu 2 divided by sigma root 1 by m plus 1 by n. This follows normal 0 1 and these two are also independent. And let me define S p square as m minus 1 S 1 square plus n minus 1 S 2 square divided by m plus n minus 2. Then x bar minus y bar minus mu 1 minus mu 2 divided by S p is square root m n by m plus n. This will follow t distribution on m plus n minus 2 degrees of freedom. So, this can be used as a pivot w, because this involves certain random variable which is of interest to us, because we wanted the confidence interval or mu 1 minus mu 2. Random variable is involved here and the distribution is free from the parameters here. So, this can be used as a pivot quantity. Based on this, I can write down the confidence interval probability of minus t m plus n minus 2 alpha by 2 less than w less than t m plus n minus 2 alpha by 2, that is equal to 1 minus alpha. Once again I have chosen symmetric because the t distribution is symmetric. So, shortest length interval will be the one which will be symmetric around the origin here. So, this probability is 1 minus alpha. So, we can simplify this statement here, probability of minus t m plus n minus 2 alpha by 2 less than w. So, w is root m n by m plus n x bar minus y bar minus mu 1 minus mu 2 divided by S p less than t m plus n minus 2 alpha by 2, that is equal to 1 minus alpha. So, after certain manipulation I consider multiplication by S p and divide by this term, then I adjust x bar minus y bar on both the sides. That statement will be then equal to x bar minus y bar minus root m plus n by m n S p t m plus n minus 2 alpha by 2 less than or equal to mu 1 minus mu 2 less than x bar minus y bar plus root m plus n by m n S p t m plus n minus 2 alpha by 2. This is equal to 1 minus alpha. So, we get 100 1 minus alpha % confidence interval as x bar minus y bar root plus minus root m plus n by m n S p t m plus n minus 2 alpha by 2. Now, remember here we have taken sigma 1 square is equal to sigma 2 square assumption here, which could have been done by making a test of hypothesis first, that is we test whether sigma 1 square is equal to sigma 2 square. If it is accepted, then we apply this method. But suppose it is not accepted, that sigma 1 square by sigma 2 square, the hypothesis sigma 1 square is equal to sigma 2 square is rejected. If it is rejected, then this test procedure will not be useful. In this case, an approximate procedure has been proposed by Welch in 19. So, that is, let me say case 3, sigma 1 square not equal to sigma 2 square and they are unknown. So, this is known as famous Variance Fisher situation. Even in the testing problem, we have not considered this, because in this case the theory of Neyman Pearson test fails. We cannot find out UMPU unbiased test in this situation. We can also not derive a likelihood ratio test in that situation, it does not give a region there. So, approximate, this is a famous Variance Fisher situation and approximate procedures were proposed, and one procedure which is based on, let me call it W star, that is x bar minus y bar minus mu 1 minus mu 2 divided by square root of S 1 square by m plus S 2 square by n. So, basically this statistic, if you see why it has been considered, you consider the case of known sigma 1 square sigma 2 square. In the known sigma 1 square sigma 2 square case, this was the statistic that we had considered as the pivot quantity. So, in place of sigma 1 square and sigma 2 square, we have replaced by S 1 square and S 2 square. So, this has approximate t distribution on say k degrees of freedom, where k is actually a random quantity. It is S 1 square by m plus S 2 square by n whole square divided by S 1 to the power 4 divided by m square into m minus 1 plus S 2 to the power 4 divided by n square into n minus 1. And again problem is that this need not be an integer. So, we usually take k to be integral part of this. So, based on W star and approximate 1 minus alpha level confidence interval for mu 1 minus mu 2, that will be x bar minus y bar plus minus t alpha by 2 k square root of S 1 square by m plus S 2 square by n. Now, another interesting case is that when the number of observations is the same and there is some sort of pairing. If there is a pairing here, then like in the pair test we had considered the quantity x bar minus y bar divided by based on the standard the variance of the differences. So, let me consider that situation also. Case 4, that is paired observations. So, as before we are considering x I y I, this is following bivariate normal. So, in that case if I am considering d I as equal to x I minus y I, that follows normal mu 1 minus mu 2 and some variance sigma d square. So, we consider d bar and S d square, that is 1 by n minus 1 sigma d I minus d bar whole square. So, root n d bar minus this is mu 1 minus mu 2 by S d, this will have t distribution on n minus 1 degrees of freedom. So, this can be considered as a pivot. So, if we use this as a pivot, then the confidence interval 1 minus alpha level confidence interval for mu 1 minus mu 2 is then d bar plus minus S d by root n t n minus 1 alpha by 2. I will end up this lecture by confidence interval for variance ratios. If I have a variance ratio, I can consider confidence interval for say sigma 2 square by sigma 1 square. Then I can consider this quantity. See S 1 square m minus 1 S 1 square by sigma 1 square follows chi square distribution on m minus 1 degrees of freedom. N minus 1 S 2 square by sigma 2 square follows chi square n minus 1 degrees of freedom, and they are independent. So, if I frame the ratio S 1 square by S 2 square sigma 2 square by sigma 1 square, let me call it W, this will follow F distribution on m minus 1 n minus 1 degrees of freedom. So, probability of course, F is a skewed distribution, but for convenience we may still consider F 1 minus alpha by 2 and F alpha by 2 points, F alpha by 2 and 1 minus alpha by 2 m minus 1 n minus 1 less than or equal to this W less than or equal to f alpha by 2 m minus 1 n minus 1, that is equal to 1 minus alpha. So, this is equivalent to saying that probability of sigma 2 square by sigma 1 square in the interval f 1 minus alpha by 2 m minus 1 n minus 1 s 2 square by s 1 square to f alpha by 2 m minus 1 n minus 1 s 2 square by s 1 square, that is equal to 1 minus alpha. So, we get 1 minus alpha level confidence interval as left hand limit as f 1 minus alpha by 2 on m minus 1 n minus 1 degrees of freedom s 2 square by s 1 square, and the right hand limit as f alpha by 2 m minus 1 n minus 1 s 2 square by s 1 square. I have discussed the general methods of finding out the confidence interval using the pivot method. I have also discussed the special confidence intervals for the parameters of normal distributions, exponential distributions, etc. Now, in this part, let me have a summary of this course. We have considered major methods of statistical inference as developed in the classical statistics. The originators of most of these concepts were primarily R. A. Fisher, and who in 1920s and 30s laid the foundations of theoretical statistics, and Neyman and Pearson, who were credited with the theory of testing of hypothesis, which I have covered in a major way in this particular course, and also the theory of confidence intervals was developed by Neyman. I have in this particular course derived the methods, that means what method should be used using what philosophy, that we have done. Now, given a practical problem, you will have a data. For example, you may have a data. So, you may treat it as a data from a normal distribution, say normal distribution with parameters mu and sigma square. Now, you may like to find out a point estimator of mu and sigma square. So, you may calculate MLEs, you may calculate Bayes or minimax estimators. You may also consider testing problems. So, you may use one of the methods. You may also like to consider confidence intervals for the parameters. You may also have say two populations, you may have samples from that. So, in this particular course we have derived all the methodologies which one can use as a statistician. I will be putting up certain assignment sheets, that is the problem sets and some of their hints and solutions for those sets, which will have actually the practical data sets there. So, from the data sets you actually solve the problem and see which method will be used. So, that will be quite useful. We have come to the end of this course. So, the topic of inference is actually very wide. I have covered only what is known as classical inference, or you can say classical statistics. There are many modern methods which are being used, but that I have not been able to cover in this particular course. But these courses will these things will be useful for most of the practical problems that people face. So, with this end we come to an end. I advise all the readers to solve the problem sets that we will be putting up.